So thank you very much. Yeah, so I'm happy to give this second talk here, which is both a continuation of the first one that I did last week, and also to some extent the continuation of what Standa told us. So there is going to be a little bit of overlap. I will skip or not, depending on whether the content is significant. So I've named this vibrational and phonon spectroscopies because this is very often what I'm looking at. Experimentally with a shameless and outrageous bias towards Raman. This is just from my own experience, right? I mean, my original experience is really from Raman, and then I moved on a little bit towards the other techniques that I'm going to talk about, including infrared, neutrons, and X-ray scattering. So before starting, I would like to just address the motivation of why you would want to look at phonons in those materials, and some people have this type of inspiring thoughts. Michel left. Michel, if you hear us, I'll find you back in Orsay. Okay, anyway, so there's plenty of good reasons to look at phonons, and actually Standa gave plenty of illustrations how phonons in ferroelectrics are connected to the properties. They are really essential to what we are doing. So I have an outline. I actually have way too much for 1 hour, so again, I'm gonna go with the flow, focus maybe on what's more interesting, but roughly I still have a first part which is about very general principles on phonons and what we want to do with them, and some experimental aspects of inelastic scattering. Then I still have this small chapter of phonon symmetry and selection rules, because of course. And then I have a couple of experimental stories that are mostly connected to soft modes. So this is something that you've heard already a lot. So what I'm going to tell you is complementary to that. So in all of those cases, I have to say that my point here is not really to tell you about the physics of the systems in details, but it's much more to show you examples of measurements that I think have some nice pedagogical value because they are done on model systems, and they can allow you more easily to understand what can be done with those techniques, in the hope that you might find it useful perhaps for your own work. And then there's a number of practical considerations for Raman spectroscopy. So this is now the very pragmatic questions that very often people have when going to Raman spectroscopy. So I will see how much of that I can address. Right, so I want to start with a super general point that sort of supports the whole idea of vibrational spectroscopy. So here it's just an example of a phonon mode in a perovskite. Looks pretty, right? And this underlying idea is that the vibration frequencies, the phonons, or the vibration frequencies of a molecule, are really a unique fingerprint for a given material at given external conditions. So they are a very sensitive probe to nearly everything. When I say material here, I of course do not mean only chemical composition, but I also mean crystal structure. So you can keep the same composition, change the crystal structure, and this is going to be reflected in the phonons, which is very good reasons to try to measure them. So with this in mind, I mean, this explained maybe 90% of the Raman spectra that you will see in the scientific literature, because as soon as your Raman spectrum or IR or anything is a fingerprint, then you can use it just for simple, say, quality control of sample processing. You can identify bonds, you can locate phase transitions, and so on. So just very simple fingerprint approach to spectroscopy, okay? So as an example, now is the time, I'm afraid, to move to the mandatory illustration of ISO 2025. No, actually not that one. The mandatory illustration is something on bismuth ferrite, of course. I mean, we all need to have something on bismuth ferrite. So this is an example, quite a pretty example of what I was just saying. So this is about bismuth ferrite films grown on lanthanum aluminate substrate, so under compression. And when you grow that on this substrate, you may or may not know that BFO may crystallize in different phases. So one of the phases, the one that's called here R1 or R2, is very close to the bulk. I mean, it's reasonably comparable. But the other one that's called T is this sort of super tetragonal phases that's strongly elongated. Okay? And of course, when you grow your film, you want to know what you have. And this is what they did here in this particular paper, there's hundreds of them, right? I mean, it's just one example where you do a Raman map and you just identify, you measure your spectrum. Here, every single P corresponds to a phonon mode, and you recognize the signature of the R phase and you recognize the signature of the T phase, and you produce this beautiful Raman map that tells you something about the results of your growth, okay? So it's extremely useful, but very much fingerprint approach. You don't need to understand much about that. You just need to recognize the pattern, okay? So typical machine learning material, I would say, those days. So of course, we want to go a little bit beyond that. So I want to make another very general argument that we will have in our perovskites or any kind of material different type of modes, and that in the first approximation, what we are looking at is really a bunch of harmonic oscillators. This is what we have. And you do remember, hopefully, that for an harmonic oscillator, the frequency, angular frequency, is given by the square root of k over m. So m, of course, is the mass of whichever atom is contributing to this particular vibration mode. Doesn't change too much usually, but of course it changes with the vibration modes that you're looking at. And k here is a force constant. So in other words, it's interatomic force constants. So what I'm saying here is that the frequency of these modes here contains the interatomic force constant. So any sort of physical phenomenon that changes the force constants is going to be reflected one way or another in the vibration spectrum, which we can measure by Raman, IR, or some others. So this makes it really a very sensitive probe to many, many things, right? So typically, all those force constants are going to be coupled to strain, to magnetism, and so on. So there's potentially a lot of physical phenomena that you can explore. So here I'm representing some phonons, just random phonons, but the full picture, of course, would be something like this. We haven't seen so many of those so far, right? So those are phonon dispersion branches. Standa had the one for, I think it was STO, right? Yeah, that you were showing. Here is another one just as an example, and I will repeat this because it's really important. So what those theory people do is that they take their favorite DFT code. In that case, it was VASP, I think, but whichever. And they compute the phonons in the cubic phase. This is for potassium niobate. And when you do so, you plot this beautiful spaghetti, and you observe in particular the modes that appear as negative frequency. So those are the ones that are unstable. So this dispersion tells you that potassium niobate at 0K, of course, doesn't want to stay cubic, but he wants to go to some lower symmetry. Doesn't immediately tell you which one, because we have actually many unstable modes here. Everything that's below 0 is unstable. So you have some at gamma, so long wavelength, but you also have some unstable mode as a down boundary. So it's not obvious from this picture alone in which phase or in which structure potassium niobate wants to crystallize at 0K. But that's a starting point, and that's also for us experimentalists extremely useful. Just in terms, as for explanation, so those labels that you see here, we've seen them last week. It was those conventional symbols for the different points in the Brillouin zone that we have seen. So there's going to be a couple of them, so I'm just warning you. So this is a ferroelectric, potassium niobate. The main instability is at gamma, and it's this sort of polar mode that Standa was talking a lot about. Here is another example with a bit more information. So this is now barium zirconate. So if you don't know barium zirconate, it's basically cubic at ambient pressure all the time, so pretty simple. But when you compute the phonons by first principle calculations, you always have a problem here. So not at the zone center, not with a ferroelectric mode. This thing is not ferroelectric at all. But you do have a problem here at the zone boundary with a mode that is like slightly unstable, below 0, above 0, depending on which exchange correlation, remember that? All those approximations that you're doing, you may bring this mode stable or not. So another information that you have on this example is a way that the people in Liège have to color code which atom is contributing to which mode. And I find it's very useful. So essentially, where you see some red, it's essentially barium moving. When you see some green, it's zirconium. And when you see some blue, it's oxygen. So, I mean, unsurprisingly, the heavy barium vibrates right at low frequency because it's heavy, mostly involved in all those acoustic-like branches. Zirconium only is dominant in some modes constrained by symmetry, and the rest is mostly oxygen. Okay? But still useful to have in mind because, of course, when we want to make a detailed analysis of what we are measuring, we also want to know which atoms are vibrating for a particular mode. I will take 1 second to go to this web page because this is, of course, still a bit abstract. So I will just take 1 second to show you what clever people have been working on. So now, okay, let me just bring this here. I mean, this is not the only tool for representations of vibration, but if you need this kind of pictorial, movie, you can have it in this way. So what I did here is just that I uploaded this dispersion for barium zirconate. It's not exactly the same, but it doesn't matter so much. And then you can just travel around the phonon branches and see which atoms are contributing to what. Okay, so pretty cool if you need this sort of visualization. Again, it's not the only tool, but I dare say that many of them tools online are limited to phonons at the gamma point, and they do not allow you to travel around in the Brillouin zone that beautifully. Okay, and then you can export this as GIF or movies and everything. It's very useful. So let me go back to the presentation. Right, okay, so we have these phonons, and this is now what we want to measure, okay, with different techniques. So, like I said, I will not cover infrared spectroscopy at all, which is based on an absorption process. Instead, I will just talk about inelastic scattering process in general. So what we have is some incoming, here it says photon, but actually anything, like incoming anything, that with some wave vector and some energy that scatters into another photon with wave vector and energy. And in the process, a phonon is typically created. So this is the underlying physical process that we have all the time, at least for the next hour. And it has to satisfy two basic conditions: conservation of energy and conservation of momentum. The conservation of momentum in particular is really important, and it tells you, when you do the math, it tells you what Standa already said, that if you're working with visible light, really only phonons at the gamma point are accessible. So this is valid for Raman, this is valid for infrared, this is valid for hyper Raman, this is valid for Brillouin. So again here, with all those optical techniques, you'll be able to travel along that line. If you want anything else, you will have to go to other probes, and typically neutrons and X-ray. Right, so just to position this kind of techniques in a sort of a broader context, I also find those sketches useful. I took them from some papers or some synchrotron websites. And so what you have here, it's essentially the same graph, just with a couple of nuances, right? So here what you have is a scattering vector, here and a frequency, okay? So imagine you have any type of excitation. I'm looking at phonons, but it can be something else. It will have a scattering vector and a frequency. And then this tells you which technique you should target depending on those characteristics. So we've been discussing about optical techniques. So Raman here, that, as I said, cannot go too far in Q, because again, we are talking about because of this conservation of momentum. So this is where here we have to go to inelastic neutron scattering or inelastic X-ray scattering. Brillouin, essentially the same sort of things. I will not mention Brillouin here, but it's roughly the same, only you're looking at acoustic phonons, so energy is much lower, but the wave vector is pretty much the same. And this I will not go at all into that, but this would be for other time scales. Okay, so pretty useful to have an idea of where you want to go. So now sticking again to visible light. This is sort of a Raman 101, or a picture that you show in a Raman 101 course. So imagine you have a system, you have different vibrational levels, and then here somewhere you have an excited electronic levels. Like I said, infrared would be a direct absorption process. So you approach your sample with a light whose energy coincides exactly with the vibrational level you're going to probe. But for the Raman process, it looks like this. So you're coming with an energy that's somewhere in between. So it should be like above that, which would be above the infrared, but also below this excited level. And then it gets excited, falls back, and depending when it falls back, you have different processes occurring. If it falls back to the same energy, it's frequent but useless for us. So this is Rayleigh scattering, elastic scattering. If it falls back with an energy loss, it means that a phonon has been created in the process, and so this would be called the Stokes scattering, and this would be the anti-Stokes, where your system starts from here and falls on the ground state. In that case, there is a phonon annihilation in the process, and your outgoing light has more energy than incoming light. Okay? So again, important thing here is to remember this underlying assumption that we are working with visible light, it's well above the vibrational levels, and ideally below any real excitation. So if you're talking about a, say, high band gap material, like our classical ferroelectrics, it works. But of course, if you're talking about strongly correlated systems with a much lower band gap, this is an approximation that's very disputable. Here is just the same. I just added another process here that I'm going to mention a little bit, just with one example, which is hyper-Raman. So what you're doing with hyper-Raman is that you're approaching your sample with a light of, say, half the energy. Two photons gets absorbed, and you're checking the energy difference with respect to this second harmonic. Okay, it's a bit more rare, definitely not common, but useful for us because it gives us access to modes that would be otherwise not easy to measure. But again, I mean, at the end of the day, whichever technique you're looking at, the spectrum that you're going to measure is something like that. So you're going to have some elastic or quasi-elastic scattering at the middle, and then you're going to have two sides with your excitations or your phonons, the energy gain side, so the anti-Stokes, and the energy loss side, okay, the Stokes scattering. So those two sides are symmetric in the sense that the position of those peaks is just the energy of your phonon. So this doesn't depend on the process. The intensity is not, because then temperature comes into play. But in principle, if you're only interested in the frequency, the energy, it's enough to measure only one side. Okay? So in Raman spectroscopy, we typically only measure that, unless we have a very good reason to do otherwise. In Brillouin spectroscopy, they systematically measure the both. Neutron as well, we would measure that. So then practical considerations come into play for that choice. Very brief words about, say, practical aspects. I mean, this happens to be the Raman spectrometer that we have. I'm not here to do any advertising. You have plenty of them on the market. They would all, more or less, give you good quality spectra. The only thing that I want to stress here is that it's basically mounted on an optical microscope. So to the question, what are the conditions for me to do a Raman experiment on my sample? My answer is, if you can put it under an optical microscope, you can do a Raman spectrum of it. Okay, so this is about as simple, at least in first approximation. Of course, those commercial spectrometers, they are a bit like black boxes. Here would be the black box opened. Again, not going to comment on, this is pretty basic experiment when you think of it. Most important part, I would say, for us is really the microscope here. And the fact that you're typically in a Raman experiment come from the top, so your incident laser is coming this way, and you're also collecting the light this way. So this is a backscattering configuration. It's of course not the only one. In principle, you can do all sorts of geometry, but for commercial instruments, this is by far the dominant option. This is for Raman. Then if you really need to go to Newtons or X-ray in order to investigate phonons in the Brillouin zone, then there's a question which one you should use. So here is a brief comparison of the main characteristics that they have. This is something you might remember from solid state physics course, because it applies pretty much to diffraction as well, right? So very roughly, neutrons, I mean, would couple strongly to magnetism. I mean, not so important for us of phonons, but of course, if you're looking at spin waves, it's absolutely important. The neutrons interact with the nuclei, as opposed to the X-ray that interact with the electrons. This is also a very different interaction mechanism. Then X-ray tend to have a small penetration depth, and neutrons really penetrate a lot. So it's more like a bulk measurement. This point here is actually pretty important, that you have some limitation in Q space, or you may have some limitation in Q space in neutrons, where in X-ray this delta is independent of Q. This is a bit technical, actually plays a big role if you're studying amorphous material, not so much crystalline material. And then from a practical aspect, for me as an experimentalist and as a user of those facilities, neutrons will really require large samples, where X-ray will prefer small ones. So this sometimes is absolutely determinant, especially if you want to measure things in situ as a function of pressure, typically. This is a very important practical aspect. If you go for neutrons, I mean, I think the first key word that you might want to remember is triple axis spectrometer. It's not the only technique available to do inelastic scattering, but it's the I would say probably the most classical. Here is just one example of what it may look like. This is the IN8 at the Institut Langevin. So triple axis because you have, well, 3 rotation axes. So your input beam here, monochromator, sample, analyzer, detector. Okay, so this is general thing. Then of course you can go if you're interested into the details of neutron optics. Again, remember that as a starting point. If you go for X-ray, this is the beamline. This is the setup of the beamline ID28 at the ESRF. Not so much different. It's just that here you have a bunch of, you have more details on all the optical elements. What I want you to pay attention to here is this. Right? So this is now in meters. So between this mirror and the sample that's here, you have about 40 meters. So why is that? I mean, you have to realize the challenge here, and this is what makes X-ray also a newer technique as compared to neutron. You're coming with hard X-ray, like let's say tens of kilo EV, and you want to measure an energy difference that corresponds to a phonon, which is of the range of, let's say, 10 milli EV. Okay, so the energy resolution that you need to get there is absolutely drastic. As a matter of fact, when I was a student, I was told that it was not possible and that neutron was the only way to go. That was not completely true at the time because those beamlines were already in development, but this is definitely newer. Okay, and I also like showing what the experimental hole actually looks like. So this is again ID28. The incident X-ray from the synchrotron source are coming here from the right. They are going like into the other room here. Then after monochromator, they are coming back. Sample is there, and the actual goniometer is this whole thing on the rail. So this whole thing have to move when you want to move your 2 theta angle. I mean, beautiful piece of mechanics. I like it. Very impressive measurements. So this is about everything I want to tell you about very practical aspects so far. I will come back at the end on some more details about resolution and size and stuff like that. But for the moment, I would like to move to, like I said, the follow-up of the first lecture on symmetries. Ready for that? There's going to be questions for you. Be ready. I have shown this image already with different types of modes, and I also mentioned that we wanted to know precisely which atoms are contributing to the motion. So this is the karaoke for you now. You ready? Okay. So let's go for that. Let's check how they. Thank you, transform. Yeah, okay, let's go for it. Okay. So exactly, so we need to check how they transform and to relate those modes to the irreducible representations that we saw last week. So here comes a part of the presentation. I left the whole slides, I mean the full thing in the presentation, so you will get them. I will not go through the whole process, otherwise we would spend 1 hour, and I also want to talk about something else, so I will just initiate it and then jump to the conclusion. That's okay, right? So the key word that you have to remember for that is that we are interested in what's called the mechanical representation. So we are interested in decomposing those vibration modes, or how atoms are displaced from their equilibrium positions according to the EREPs. Okay. I will just start the process so that you understand what that is. So I take again like a simple case, just H2O, I mean not super relevant for us, but only 3 atoms, so makes it more simple. And also this nice MM2 point group that now you know by heart, okay? So all the atoms have their equilibrium position, and I can imagine that I'm taking them off their equilibrium position, which gives me 9 degrees of freedom, like 3 atoms in 3 directions in space. So if I want to describe this in a vector space, and I know nothing a priori, I can just choose a canonical basis of vector, like my first eigenvector would be displacement of oxygen along X, for example. Second vector would be displacement of oxygen along Y, and so on and so on. So I get 9 vectors, okay, meaning that my matrices, or my space, is of dimension 9. So my mechanical representation is of dimension 9. So if I wanted to write it explicitly, this is how it would go. We never have to do that. I'm just flashing this example to help making this representation theory a bit more concrete. So here I'm writing the matrix of this mechanical representation associated to the mirror plane My within the basis that I have just described, which is a canonical basis, but absolutely not adapted to symmetry. So let's take a couple of examples. So if I take a displacement of oxygen along Z, it goes there. I apply my mirror plane NY, doesn't move. Okay, and this was my third component, so I have a 1 here. If I consider displacement of oxygen along Y, I apply my mirror plane. This one is reversed. So this coefficient here is a -1. If I go to the hydrogen, then of course when I apply my mirror plane, this hydrogen goes here. Okay, so I also have to take that into account. So this one goes here, and the arrow, the meaning of the arrow is reversed. You check in which order I have chosen my vectors, you realize that this would correspond to this -1 coefficient. Okay, so this is in principle what I can do, but again, we never do that because mathematicians have treated us with better ways to do it. Can you say it with me? Thank you, math. Yes, great. So in practice, what we have to do is to reduce this representation, and there's two ways to do it here. One that is very general, and that's based on those orthogonality theorem that I alluded to last time. It's not very much unlike decomposing any vector on a basis of orthogonal vectors. But there's another method that's cute, that's called the correlation method, and that's really well adapted to the vibration problem because it allows you to track really by hand which atoms are contributing. So this is what I like. I will just give you the general idea of this method, and then I will jump to the conclusion. Again, too much text on this slide, I know, but this is just so that you can have it and you can read it for yourself later. So the general idea of this correlation method is to say, okay, I'm an atom, I'm sitting in some position. I know my local symmetry because I know which of the symmetry operations leave me invariant, okay? And I also can tell from that easily how my displacement along one direction transforms in the irreps of that local symmetry. Okay, so this is very easy. You just have to read it from the character tables like we did last time. So now what we have to do is to take this information and to see how this information that relates to a subgroup of the group of the molecule transfers onto the irreps of the group of the crystal or the molecule. So if you remember last week, this would be the induction side of this group-subgroup relation. And this is what I do not want to go into in details for now. I still give you the recipe, like step by step, just have to follow step number 1, 2, 3, 4, 5, 6. It's believe me, it's super easy. It's just that I detailed everything in like so minutes. And I jump to conclusions, which is gonna be that, okay? So here I represented the final solution for this water molecule in that way, that I took the eigenvectors. So this is now my symmetry-compatible eigenvector, and we assign them to one particular symmetry. So this one is A1, again, the totally symmetric representation. And you can see, I mean, you can check for yourself that indeed if you apply all the symmetry operation, it is invariant, right? It doesn't change. This is also valid for the second mode, this sort of anti-symmetric stretching. And the other one, the only one that's not totally symmetric is this B2 here, okay? It's the one that involves some displacement of oxygen along whichever direction that was, okay? And then you can check that indeed if you apply the 2Z operation, then it's reversed. So this is just a graphical representation of the character table. Just take this as a 1, take this as a -1, and you find it again, okay? So I have my 3 vibration modes, and I know how they transform. With the correlation method, I can actually do more. And here comes an important comment to the eigenvectors. So here are, again, my eigenvectors, okay? And here is what the real result of the reasoning would be, okay? So where I not only have my final result that tells me I have 2A1 mode plus B2, but I also have tracked along the way which atoms are moving along which direction. And if I consider B2, I'm actually in a very special case because I only have one mode that transforms like an irrep of dimension 1. And when you're in this situation, it's very cute because those directions are really completely constrained by symmetry. Okay? So the way you would do it is to go up again in this table and identify which atoms are moving along which direction. This is not the case for the two others. Okay? For the two others, I have two modes. So A1 has dimension 1. This is fine. Oops. But I have two modes with this symmetry. So that means that those two vectors, or those two displacement patterns, are only one possible basis of symmetry-compatible eigenvectors. We sort of know it's there because then we put some additional physical knowledge that tell us that it has to look like this. But any linear combination of those two would also be compatible, would also transform like A1, so would also be compatible with this. So this is I think really important to understand because you see those vectors very often. So if they come from calculation, of course, fine. But if they are derived from this sort of symmetry argument, it's good to remember that they are not the solution, but they are a symmetry-compatible solution. Does that make sense? Yeah. So because I know you're going to get bored on the bus, on the plane, here is a small exercise that you can do. So here I just took a square. I solved the problem for you, so giving you directly the final results. And we are actually in one of those very nice cases where I have many more modes, but like those four are there's only one of each, and each has dimension 1. So the argument that I just mentioned completely applies to those ones. The EU modes is a bit different because this one has dimension 2, so it doesn't work exactly like that, but you can do it. Okay? So have fun. The solution is going to be at the end of the slide, so you will get them when they are uploaded on the server. Right, so this is the way to go. Again, I mean, water molecule and square are not super relevant for us. Some people are actually not lazy, so they do it for perovskites. So here is what it would look like. So this is taken here from a paper some time ago, and this applies to a perovskite that has the PNMA structure. So it's this orthorhombic structure. The unit cell is multiplied by 4. So you have 20 atoms per unit cell, 60 phonon modes. So the mechanical representation would have dimension 60. That's the reason I didn't take that example to show you the matrix, because it becomes a bit unbearable. Okay? But essentially, they did the same job. So here you don't have all 60 of them, right? First thing, because 3 of them are acoustic modes anyway, and you don't care. And second, because they were doing Raman experiments, so they only retained those modes that are active on Raman. So I will come back to that in a second. So again, this here, this, by the way, is not just a movie. I mean, this is the result of a DFT calculation. Okay, so there is some physical foundation to it. This is more of a concept of eigenvectors, where they decided, of course, to make something that's say clear. So they completely ignored the distortion of the octahedra. They represented them as if they were not tilted, but of course in reality they are. And then they also separated the motions of atoms clearly. Like on all those modes, you only have A cations moving, and on this one it's only the oxygens, okay? Who has already identified my movie in this table? It's there. Seconds. Someone, it's not that difficult. This is a typical breathing mode. You see the octahedra are really breathing, and it's actually like this one if you look at it. So they breathe in antiphase, so one is expanding and the other one is shrinking. Okay. So now I know how, yes, sorry. Yeah, so acoustic mode in that case shows up as identical translations of all atoms. So actually you can see them on the web page. I mean, not going to do it for the sake of time, but the acoustic modes are there, and you will see that it's just all atoms vibrating like this. So now I know how my vibration mode transform. I still need to relate it to what I can measure with infrared and Raman. Here, also for the sake of time, I'm only giving you the final results without giving you the underlying theory. I think for infrared active modes, it's pretty easy to understand, because it's an absorption process, so the The oscillating dipole moment of your mode interacts directly with the polarization of the light. So what you have to say in the language of group theory is that a vibration is going to be infrared active if it transforms like a polarization vector, okay? Or if its symmetry is that of an irrep associated to a basis function x, y, or z. So again, take your character table, check them, you have them. Raman active modes, that's maybe sometimes a bit more difficult to grasp, because what has to be modulated here by the vibration is not the dipole moment, but it's the polarizability, okay? But if you do that, you can formulate it exactly in the same way, and you can say that vibration is Raman active if it transforms like a second-rank tensor. That is to say, if its symmetry is that of an irrep associated to a basis function, one of these, so one of the second-order polynomial. So following that, I mean, there's a number of rules that, that you may or may not find useful in your case. I think what's important to remember is that you can have a little bit of everything depending on the crystal symmetry. So if you take one mode, it can be visible in Raman and IR. It can be visible in Raman only, in IR only, or it can also be what we call silent, so not visible in either of those techniques. And this is, of course, a bit of annoying, but it does happen. Then you have some more details. I'm not going to go into that, except to say maybe that in our ferroelectric materials, most modes typically in the ferroelectric phase are both active in Raman and infrared in general. So you tend to, you have the freedom to choose the technique that you wish. So just as a practical example, so again, this is something that you can directly read from the character table. So if I want to do this exercise for my MM2 point group, which would be, okay, the water molecule, but that would also be potassium niobate at ambient conditions. Then you see that if I want to measure a mode that transforms like A1, I have to arrive with an infrared light that has polarization along the z-axis, so the polar axis. But I can also measure it with Raman and with the polarization, incident and scattered polarization along x, y, or z, irrespective. Okay, this is how you read this information from the character table. This here is the one that applies to the PNMA perovskite I was showing. So the point group here is MMM. And it's sort of a bit more simple. I mean, this one is a bit deceptive in the sense that you have the second order polynomials everywhere. So all those modes are visible in Raman. Yes? Yeah, absolutely. Like everything I'm saying so far is really only at gamma. Yeah, I was saying this is a bit deceptive for Raman in the sense that all the modes here are visible in one configuration or another, so it's not very selective, but if you look at those PNMA perovskites, it gets a bit more interesting. So here you have 8 classes, you have 8 irreps, and those second-order polynomial, they are only present here in all the irreps that are labeled G, like gerade, because they don't break inversion symmetry, okay? So this is already nice, but what's even nicer is that those symbols really gives you almost directly the scattering geometry that you have to use if you want to measure them. So this is what it looks like here. Oops, where am I? Sorry, yeah, so this is what it looks like here. I take an example of an orthorhombic PNMA perovskites. There's like hundreds of them, but here it so happens to be samarium ferrite. So you have to imagine that I have a crystal like this and that I place under my microscope. And of course I'm coming with my light from the top here. Incident light comes from here, so its polarization can be along y or x, and then the scattered light can also have polarization along y or x. So that gives you 4 configurations that you might want to try. So this symbol here, it basically tells you this polarization and exactly what I said. So here that means incident polarization along y, scattered polarization along x. What you see are the modes with B1G symmetry. Okay, this again is directly read from the character table, and then etc. So you can see that this works in that case really nicely, that the peak that's visible here is completely invisible in the other configuration, etc. Okay, so this is a nice example of what you want to do ideally when you're measuring the phonon modes. Okay, does that make sense so far? We are done with symmetry.
Maybe you can explain what GAU means.
Yeah, so this, let's go back to, it's useful. So this G gerade, so in German even, right, means that you're not breaking inversion symmetry. And those will always be active in Raman. U ungerade, so is your breaking inversion symmetry. This is something that you can realize if I go back one step. Yep, like here. Okay. You will notice, for example, so those are only Raman active modes, and you will notice that the B cation, the one that's at the center, never moves. This one is always fixed in all the modes. This is because moving would break inversion symmetry, so it would make the mode infrared active, but not Raman active. Okay, I was really expecting a oh when I said we were done with symmetry, but okay. So let me then start with a couple of thank you. Who did that? Yeah. So let's continue with some stories, and like I said, they are largely based on soft modes. So I have 3 of them. I mean, we'll see. I might skip 1 or 2. I mean, depending. So this one I called like imaginary frequencies, really. I mean, I've shown you phonon bands calculated by DFT, and they show us negative frequency. Well, they're actually imaginary, of course. In experiment, this is not what we measure. So let's recap a little bit what the picture is here. So this is what DFT tells us. Okay, so they compute phonon frequencies, they find an instability, and they find a particular phonon frequency that's somewhere like here. And then, of course, you can sort of add a temperature effect to that and renormalize this phonon frequency so that it's going to increase, and ultimately it gets positive, and then, of course, your structure becomes stable. So this is the theoretical picture that you would have. Now, of course, I mean, I live in a world where frequency don't get negative. So what happens is that this works well, but then, of course, what happens here is that you switch to the low symmetry phase. So the phonon frequency renormalizes here and goes up again. Okay, so this is what you expect in real life. So this would be the para phase, and this would be the ferroic phase. It doesn't have to be ferroelectric; can be also ferroelastic. So the first example that I have, I mean, is lead titanate. That to some extent you have seen with standard already. So I'll try to make it maybe a bit shorter. So just as a reminder. Lead titanate, typical dysplasia ferroelectric, only one phase transition, super nice, cubic to tetragonal with a critical temperature at 760 K. In terms of phonon modes, we have this relation. So this is the phonons that you would get in the cubic phase. Those 3 are infrared active. This one is silent, bummer. And those go into those modes in the ferroelectric phase. I wanted to make a comment here that's related to the eigenvectors before. So those you have seen in standard, well, actually, you have seen them here. So let me see, because in principle it should work. So it's drifting because I'm shaking a little bit, okay? But those are the modes that you have seen like 1 hour ago. So you should remember them, okay? So here, the comment that I want to make is again that as it is represented here, you see that it's very clean in the sense that it's separated into modes in such a way that, for example, the lead only contributes to that one and not to the others, okay? So this is clearly a proposition for a symmetry-based basis, okay? That, of course, completely makes sense because we know the system for a while, but that is, from a symmetry point of view, only arbitrary. So sometimes you might have mixing between those 2 modes, and especially when you vary pressure or you vary temperature, you might have also a gradual change in the actual atomic displacements that are associated to the phonon. So this should be really seen not as something intangible and fixed by symmetry, but only as a base on which you can analyze your atomic displacements. Okay, so this you've seen. So let's see here what group theory tells us. Well, actually, you had the results already. This is again taken from the Bilbao server that now you know by heart, and you can find essentially that those modes get activated here. So just jumping to the conclusion and the techniques, here is what I would say for the different techniques that you might use if you want to look at those soft phonon modes. Below TC, infrared is perfectly fine. Raman works too, because like I said in ferroelectrics, very often they are active in both. Hyper-Raman doesn't. It's not for symmetry reason, but it's just that as soon as it's ferroelectric, you're blind because you have so much second harmonic generation that you cannot measure this very small shift, okay? If you go above TC, infrared, I say okay-ish, in the sense that symmetry-wise it's allowed, but we're talking like quite high temperatures already, where modes tend to be smeared out by temperature effects, so you can measure them, but it may not be the best technique if you want to have a nice accuracy. Raman doesn't work. I mean, the modes are not active in Raman, so that's it. This is for symmetry reasons, but this is where hyper-Raman comes into play and can be a very nice complement. I will actually skip directly to that because you've seen many similar data with standard, so I will skip the Raman part and I will go directly to what a hyper-Raman spectrum looks like. This is from a paper by Jirka, all together with the guys in Montpellier who have this beautiful setup. So this is what hyper-Raman spectra look like for lead titanate above TC. Yeah? So everything again is above TC. Below TC, you're blind. You can't see anything. So what you see here is a very clear soft mode behavior in the sense that you have a bump here that goes quietly to 0, right? It's definitely not as nice and sharp as you would get in proper Raman. That's okay. But it still allowed them in this paper to make very nice fits off of the soft mode behavior. And then you will find this discussion on how the damping changes across TC and so on. Not going too far into the physics, but this is really to highlight this measurement because to me it's one, and I'm not saying this because Jirka is in the room, but to me it's one of the very, very beautiful determination of soft modes above TC in lead titanate. I will also skip this part on barium titanate because Tanda mentioned it quite a lot. But I would like to have another example, which is now related to not only polar and anti-ferroelectric soft modes, but not only ferroelectric soft modes, but polar and antipolar. So now I'm not looking at gamma only, but I'm interested at what happens along the dispersion when I move to gamma, so zone center to the zone boundary, okay? So this scenario here, this sketch A describes what you would expect for a ferroelectric phase transition. So you have above, where is above TC? You have here. So when you go to TC towards the transition, the idea is that this phonon frequency goes down until it's unstable and then it goes up again. But this one doesn't really feel it, the one at the zone boundary. So again, very simply in terms of atoms, I don't have this picture, but probably you can picture it. So like the ferroelectric soft mode would be this one, and the antipolar one would be this one. Okay, this is what we're looking at. So this is the scenario for a ferroelectric transition. This is a scenario for something that's an anti-ferroelectric if we want. So here you see that it's basically the same, except that the mode softening is the one at the zone boundary and nothing happens at the zone center. So it's something like an ideal anti-ferroelectric soft mode, if you want. It's sort of hypothetical in the sense that we haven't really found any real example of that. And below are two cases that represent what happens more often. This is what happens for incommensurate modulation. So here, in that case, the mode that goes to 0 is neither at gamma nor at the zone boundary, but it's somewhere in between at some incommensurate position, and this leads to incommensurate phases. And finally, and this is the scenario that they discuss in this paper, for this anti-ferroelectric, classical anti-ferroelectric like zirconates, what happens is rather that the whole branch is shifting up and down, okay? But you don't really have that. So I want to illustrate this now with an example I've been working on and that got us very excited. It's a crystal that's completely useless, okay? From the point of view of any application, it's completely useless, but it's sort of beautiful. Hello? Okay. And we were choosing it because we were exploring this possibility of antipolar soft mode. So, nice, huh? You like it? Yeah. Terrible chemical composition, it's called francesite. I mean, it's not that terrible when you look at it. So you have, it's a layered compound, okay? So you have some copper oxides here, and they are arranged in sort of a pseudo-Kagome lattice, so there's also magnetic properties associated to it, but I'm not interested in that. And between the planes, you will have some bismuth, and you have some SCO3 ions, and then the little green ball here is a chlorine, okay? And it so happens that, I mean, this crystal has a terrible chemistry, but it has a very simple phase transition. So what happens is that if you look at it from the along the B direction, so everything is nicely aligned above TC, like, and when you cross TC, which happens to be 115K, what happens is that the especially the chlorine, you can just pay attention to those ones, they move in antipolar fashion, okay? And that's all. So there is just a doubling of the unit cell that's associated to this antipolar fashion, but otherwise there is nothing else. There is not even a change in point group, so to relate to what Jirka said during his talk, it's not even a ferroic transition. There is no change in point group in that one. So in terms of phonon bands, because we did that, this is what it would look like, calculated, by friends, but it's also in the literature anyway. So complicated, we want to pay attention to gamma, of course, so the zone center, and to Z, which is the zone boundary that we are interested in. Okay? And what we see here in the calculation is a band that looks really flat. So this is a typical situation when you're when you're studying the stability of this compound. That's a bit puzzling, because you say, okay, I have two instabilities. They have approximately the same, the same energy, as in they are equally negative. So which one is going to win in real life? It's really not obvious to say, and it's even not possible to say, I would argue, from this alone. So just to put some numbers in for those who want, so the high symmetry phase has this particular symmetry. This is what you would get if you condense the polar mode, so if the phase is ferroelectric, and this is what you would get if you condense the antipolar mode. So if this one wins, the ground state is technically this one, because it has lower energy, but then this one is like 3 MeV per formula unit above, which is essentially degenerate. Okay, so at the level of accuracy of DFT, it means nothing. So our purpose with that was precisely to go and explore the modes at those points, and so we had to do it. And the reason I like it, without going too much into I'm actually going to do that without describing too much the details of who does what. What I really want to stress here, and the reason I'm happy with it, is that we really had to combine 3 different techniques to get this full picture. Okay. So if I want the mode at gamma, well, gamma is easy optical technique, so we could do IR and terahertz, and so this is what would give you this mode here. That does soften a little bit, but it doesn't get to 0, and then it hardens again. Okay. But for the Z point, so in the low symmetry phase, symmetry allows it in Raman, so this was quite easy to measure. But above, it's at the zone boundary, so you can't access it anymore by optical techniques. So this is where we needed to go for inelastic X-ray. And why X-ray? Because of crystal size, typically. In principle, of course, there's nothing wrong with doing naked neutrons, but we couldn't. I leave it there. Again, I don't plan to go into the details of why they behave this way, but I really want to stress that it's one of those examples where you need a combination of different techniques to get the full picture at gamma, at the zone center and at the zone boundary. Make sense so far? I'm hesitating now on which one, what do you want? What do you want? Because I have another soft mode. Oh yeah, well, this one is more likely to have me shake on the stage, so that's why I guess you're interested. I see. Okay, so I will give you this story. I will try to make it a bit faster because of time. So tilts in perovskites. This is the cubic perovskite, like barium zirconate that I was talking about. I am not talking about ferroelectricity. I'm only talking about the tilts of the octahedra, so I'm talking about ferroelasticity. Okay, so there is a tilt angle, there is a strain, but there is no polarization. Now, there's many ways that you can tilt this octahedra together, and of course this is known, this has been studied for a while, so we know exactly what kind of tilt leads to what symmetry or ring, okay? So this here would be the PNMA perovskite, not the best picture, and this here would be an image with just tilt in phase in that direction. Okay? So this is the general context, and this is now how barium zirconate was of interest for us. So here is a bit more of context. So it's cubic at all temperatures. Melting point is really high, so that's why it was difficult to get good quality single crystals, which has hampered the research for a while. But eventually, a PhD student in collaboration with thousands of people did that, and we could get our hands on single crystals. So going back to the dispersion now, you remember, you've seen before in the first slide, you remember I told you about this small unstable mode here. So it's a mode that's unstable but doesn't show in experiment or doesn't show in real life. So the question becomes, is it really that, DFT is not calculating accurately this particular case and that some other approximation needs to be done? Or is it that the crystal maybe is cubic on average, but we might still have some kind of a local tilts that just don't make it to a macroscopic symmetry breaking? Anyway, the point was to measure that one. So we are not at gamma, so no way to use optical techniques. And for this one, we actually did both. We did X-ray and neutrons. So I'm going to flash a couple of those maps that you can see. So this is an example of phonon dispersions mapped by neutrons. So this is the ILL. Okay, this is going to zoom on the relevant part of the dispersion. Here you have a bit more. This is the acoustic branch, by the way, for those of you who are asking about the acoustics. And the mode that we see here and that we expect, of course, does not show up as negative, but it's here. Okay, so we can still see it quite nicely here. All those crosses that you can see are what the Newton people call spurion. Okay, so it's absolutely not physical. It comes from some. It doesn't come from your sample. Is the point? So that's why you can cross them out. So this is what measuring dispersion looks like. So what is a bit unusual on this plot is the damping, really. So typically, in a very nice crystal, you would be able to follow the branch in a much easier way. But here we are talking about a crystal that's quite small by Newton standards. So counting time was really an issue, and also the mode is really damped. I still want to show you again, just for, say, pedagogical value, selection rules like in Raman work in Newton as well. I mean, you do have some. And I'm sorry for the poor quality of the graph. This is typically the kind of data that you never show, you never published, so you never take the time to make a nice fancy plot, but at least you can see the result. So this is my famous tilt mode, the one that's supposed to be unstable. This is an energy scan. And you have two modes in there, right? So you have one that's here, that's quite sharp, and you have another one that's there and that's much broader. This one, essentially those two have been measured in different points in reciprocal space. And if you forget about symmetry and you measure it along this, around this yellow Bragg point, you don't see the mode you're interested in at all. So you have to move away, okay? So this is just to mention that there are also those selection rules in neutron. And yeah, ideally you try to think about it before the experiment, if I'm being honest, but somehow we didn't see that one coming. Same thing applies to the branches. So here I don't have the measurements to show you, but I can show you some simulations of inelastic neutron scattering cross-section. So here you can see that from my mode, I have two branches, okay, that come out of it. And in the experiment I was showing you that there's only one. So the question was, where is the other? And again, it's a question of scattering plane. It's a question of sample geometry. So if you choose your right geometry, not going into the details, you can see it. We actually did this measurement as well. I have the data somewhere. One plot that I like very much, I told you we did both neutron and X-ray, and this is the result. So there's quite a number of things to comment here. So we are still looking at this point, and again we have those two modes. So one, if you remember from the dispersion, is essentially the acoustic branch, and it's the one that involves mostly the barium motion. Okay, so this one is heavy. Okay, so this is essentially what you see in X-ray because it's the heaviest. It's the heaviest element in the perovskite. And the other one is the tilt mode, so the one that involves only oxygen. And this one in X-ray, I mean, if you do a FITS, you can see it, but essentially it's really not strong at all, right? So if you only have that, it's a bit doubtful. But in neutrons, it's like shows up like super nicely. Other comments, look at the resolution here. The blue curve is the X-ray again. Experimental resolution, 3 MeV. That's not great because this is, I mean, essentially the width here is really only instrumental. So you really cannot say much about the width of your phonon at all, but you do see that the peak in neutron, even if it's not the best, it's really much sharper. So if you want energy resolution, you have to go for neutrons. There's no way around it. This one is not as sharp, but this one doesn't have to do with the resolution. It has to do with the dispersion and the resolution in Q space. So this is another issue. So I commented on which atom contribute. I commented on scan. Of course, neutrons are expensive, so we don't measure, in that case, everything, right? We limit ourselves to a narrow energy range, where in X-ray they can take a bit more time. I didn't make the calculation exactly on how long the spectra take, but I dare say you would have like 1 order of magnitude between the X-ray spectrum and the neutron if you want to cover the same energy range, give or take. And in terms of sample size, I was mentioning our crystal here is really small by Newton standards, so pretty challenging. For X-ray, what they want is essentially something that's suitable for single crystal diffraction, so something lamella of 20 microns or something like that, depending on absorption, is what they want. So this is much, much, much easier to prepare. So that was another soft mode. Okay, right. Then we did with temperature and so on, but again, I don't plan on going too much into the physics of it. I've got 10 minutes left. It's going to be heartbreaking, I'm sorry. Okay, I want now to show, I have more about symmetries, but I will skip that, and I will try to address this story instead. So this story is both about physics and both about instrumental aspects. And this is what I call here towards resonant Raman scattering. And it addresses the question whether the laser, the wavelength that you're using in your experiments matters or not. In first approximation, it doesn't. Like if you allow this, the sketch that I gave you at the beginning of the talk with just those energy levels, it's completely, we don't care. Also, if you go in a classical description of the Raman scattering process with the modulation of polarizability, we absolutely don't care. Of course, in reality, you do care quite a lot. And there's two reasons why you care. Some of them have to do with the technique, so like purely, instrumental aspects, and some of you have to do with the physics. So of technical implications of changing wavelength, I mean, this is going to change your resolution, your resolving power, your spectral range, those things. So those are experimental details that you have to think over. It will change your intensity also in general, and also it may lead to a change in optics. So if you want to do Raman with UV, typically the normal microscope optics is not going to be suitable, and you need some adapted optics. But those are, I mean, mundane issues, okay? So they exist, they are important, but they are mundane. The other physical aspects is that you need to remember that when you're doing this experiment of Raman spectroscopy, you're sending a laser onto your sample, and the Raman effect, the Raman scattering, has to compete with everything else, like all the other phenomena that might lead to ejecting photons. And this is where typically I like showing this very much. So this is something we measured on our Raman spectrometer. It's gallium arsenide, okay, so not a perovskite at all. And we measured it with 3 excitation wavelengths. And here it's not Raman shift, okay? It's just the absolute energy of the photon that you measure. So this is measured with green laser, this is red laser, this is infrared laser. And this, of course, at an energy of 1.4 or something, is the photoluminescence that comes from just the band gap emission of gallium arsenide. Okay, so of course, we know it should be there, right? But this is not what we are looking for. So where is the Raman?
What is this intensity plotted?
Sorry?
What is this plotted intensity?
You mean in terms of counts or?
It's photoluminescence.
It's photoluminescence, yeah. This is photoluminescence. And this, by the way, you recognize because its position in absolute energy doesn't change even if you change your excitation energy. Yeah, so this thing doesn't work anymore. So Raman is here. Okay? So that's this, that, and this. So if you now plot this as a Raman shift, meaning as an energy difference between incoming and outgoing photon, then you realize that those very small peaks, they do superimpose. So this is the Raman mode that I'm looking at. But I mean, look at the competition they have here, right? So if your sample has this sort of photoluminescence, of course, you want to move away from it. And if you're too close, as you can see here, well, the colors are not great. I hope you can see, but like for the infrared excitation, your Raman peak falls already in the foot of the photoluminescence, and it gets like really weak and not great. Okay, so this is one of the practical reasons why wavelength matter. There is this other very nice example as well that was published some time ago by Jens. It's a particular system, but it's a nice example on why you want to choose your wavelength carefully. So here what we're talking about is this sort of structure. So the topic was integration of barium titanate and silicon and so on. So we have a stack with silicon, yttria, cerium oxide, lanthanum nickelate as an electrode and barium titanate. Okay, so this is what you have. And what they did in this experiment is that they did it with different wavelengths. Okay? And what you see very much depends on the wavelength that you're using. So let's get to it. So below here, those are reference spectra that have been measured on pure, powders, pure compounds. And those are the spectra that you can measure on this sort of multi-layer. And you see that they are really different, like really. So if I take the first one, so this is excitation at 325, so this is in the UV. I think it's 3.8 EV or something like that, but anyway, it's above the band gap of barium titanate. So you're coming with your UV laser and you're hitting barium titanate above the band gap. So it basically absorbs everything, so you're blind to everything that's below. So what you see here is essentially one peak that does correspond to your barium titanate here, and you don't see the rest. Quite cool. Then maybe easier to understand is this one, the red laser. So red laser is clearly below the band gap of barium titanate, so you really go through, but then it gets absorbed by lanthanum nickelate. Okay, so here you hardly see barium titanate at all, but you do see, where is it? It's here. You do see the peaks that are characteristic of lanthanum nickelate. Okay, and same thing happens for the blue laser, which is sort of like in between. In that case, it's the cerium oxide that shows up. Okay, so this is a nice example. Of course, it's a lucky, it's a lucky combination. It's not like you can make it happen every time, but it's a beautiful example of how the difference in absorption of your layers can cause differences in the Raman signal. So when you're measuring something like that, you should really think, and going for this sort of multi-wavelength is really useful. Then you can, of course, once you have those signals, you can try to analyze them a little bit better. I will move more quickly on that. So this would be a comparison of, say, pure lanthanum nickelate, as in thick film, and the lanthanum nickelate in the multi-layer. Okay. So overall, it corresponds pretty well, except that you see this E mode. E mode's dimension of the E rep is 2, splits into 2 modes of dimension 1. Okay. So this indicates that there is a phase transition happening in the lanthanum nickelate layer. The A1G mode, A1, E rep of dimension 1, doesn't split. I mean, it can't. It already has dimension 1 only. It shifts a little bit. Well, a little bit by 10 wave numbers, so that's not completely negligible. And this E mode splits as well. Okay. So conclusion: we have strain that we can quantify more or less like that just by checking how this mode shifts, and we have a phase transition that's clearly indicated by the splitting of those modes here. And same thing would go for the cerium oxide layer and the barium titanate. You can go and then try to essentially interpret this Raman shift in terms of stress that the layer is under. Okay. So this is cute, but again, it's only playing about the absorption. So I would like in the last few minutes to hopefully convince you that there is a bit more physics in there that we are trying to dive into. So for that, I will go to this sketch again, so you've seen it. Infrared again, classical Raman. Laser energy is somewhere in the middle and should be independent. But when you really start hitting a real excited electronic level, then things change. Okay? They change experimentally, you see that, but they also change in the quantum theory of Raman scattering, where you see that some terms become clearly dominant. So your light and your phonon starts coupling with some specific electronic levels. So the dream here is to say, we have a scattering process that now involves a particular electronic level, so the Raman spectrum should contain information on both the phonons, which we know anyway, and said electronic levels. So this is what we've been trying to do for some time now, and this is, I'm sorry, this is BFO again. Okay, let's go for BFO. So this is a number of spectra on a bismuth ferrite single crystals that have been measured with a number of different wavelengths. And so we see different things. Actually, I really will point out mostly what you can see here. What you can see is really changes in the intensity ratio between different peaks. Okay, so when translated into the quantum theory of Raman scattering, this means you're changing your matrix elements and the coupling of one phonon with one electronic level. So experimentally, to us it's clear there is information there. We still don't understand it. I mean, this was published in what, 2016, geez, okay. We still don't understand it in detail because those things are also pretty complicated to address from a first principle or from a theoretical point of view, but we are working on it. And in doing so, this experiment was done by combining two labs. It was very painful, actually, to collect those experiments together. But now we can make a use of also the progress in laser technology, because, I mean, traditionally you would, of course, buy one laser with a single wavelength to do your Raman experiment. But now, I mean, this is not from me, of course. I mean, this was a patient person did that for Wikipedia at some point. I'm very grateful. And this dates back from a couple years ago, so I guess it must have changed already. But the point is that laser technology is really strongly driven by quantum technology right now, and they are really making a lot of progress in many things. So you can get basically any wavelength you want by now, and in particular you can also get lasers that are completely continuously tunable. And so this is what we started working with some time ago. So this is just a visual representation of the bandwidth that this particular laser can cover, so from red to blue. Unfortunately, we have some blind zones here that are just linked to the technology of the lasers. So this is the work of my student Angelina, who was sitting there where you are 2 years ago, and now she's trying to make sense of all this data, and she likes taking those pictures of the setup when they changes the wavelength. So the idea here is that we are now able to do that really in a continuous way. And I will just show this as a conclusion. Very briefly, this is again bismuth ferrite. Here is a stack of all the Raman spectra that you can see with this time really many more wavelengths. And we can identify things like Raman resonances that are now clearly located in energy, and with the possibility to do this analysis for every single mode ultimately and really get into the tiny details of electron phonon coupling in that case. So this is sort of the dream. I do believe that there's going to be a lot of progress in that direction for oxides. I have to finish by mentioning that what I'm saying here is in no way exotic. I mean, this is something that's been used before. It's very common in carbon nano-objects, nanotube, graphene, 2D materials, and the classical semiconductors. So I'm not talking about something exotic, but I'm talking about something that has not yet reached its potential for oxides, I would say. And with this, I'm hitting the 1 hour, so I will stop here and take any question. Thank you very much.